Welcome back. We're going to continue by looking at an example of the concepts. In particular, we're going to look at an example of a conceptual hypothesis test. There's no real context to this example, but we're going to look at this so that we can identify the various components of a hypothesis test and demonstrate what we mean when we say that unusual values of a test statistic will cause us to reject the null hypothesis. So consider the following hypotheses about the mean mu of some population of interest. So we have this two-sided test, the null hypothesis, which says that the mean of the population mu is equal to some hypothesized value, which I'm denoting by mu sub 0, against the alternative hypothesis that says that the population mean is not equal to that hypothesized value. Now let's let x bar be the mean of a random sample of size n from this population. Now x bar, the sample mean, is a point estimate for the population mean. All right, it's a statistic, it's a random variable, it's computed from a random sample, and so therefore it has a probability distribution. And that probability distribution is called its sampling distribution. Now, if we're sampling from a normal distribution or a normally distributed population, then x bar itself will be exactly normally distributed. If the population is not normally distributed, but if the sample size is large enough for the central limit theorem to be applicable, then x bar will be approximately normally distributed. Now, the mean of the sampling distribution of x bar will be mu, the mean of the population that we're sampling from. Whatever that mean happens to be, that will be the mean of the sampling distribution of x bar as well. And the standard deviation of the sampling distribution of x bar will be the standard deviation of the population we're sampling from divided by the square root of the sample size. So, what we know about the sampling distribution of the sample mean, x bar, is that it's at least approximately normally distributed, and we know for a fact that that the mean of its sampling distribution is exactly equal to mu, the mean of the population we're sampling from and about which we want to make an inference, and its standard deviation will be equal to sigma over the square root of the sample size, where sigma is the standard deviation of the underlying population. So what this tells us is that while the sample mean is a random variable, it will vary around the mean of its sampling distribution, which is mu. Furthermore, if the null hypothesis is true, in other words, if mu is equal to the hypothesized value, then the mean of the sampling distribution of x bar is equal to mu 0, and so x bar will vary around mu sub 0. And in particular, the sample mean will be, again, at least approximately normally distributed, and the mean of its sampling distribution will be mu sub 0. So if the null hypothesis is true, then the sampling distribution of the sample mean, x bar, will be centered right at mu sub 0. And so that's what we're talking about here when we say that if the null hypothesis is true, then x bar will vary around mu sub 0. So with that in mind, let's ask ourselves the question, what values of the sample mean x bar would be inconsistent with the null hypothesis? That is, what values of x bar would be unusual or unlikely to occur if the null hypothesis were in fact true? And the answer to that question is values that are what we would call probabilistically far away from the from mu sub 0. All right. Now, note the following. We have a probability statement here, and this is just quantifying what we're talking about here, quantifying in probabilistic terms. What this is saying is that the probability that the sample mean is between these 2 points, this lower endpoint here on the left and the upper endpoint here on the right, the probability of getting a hold of a sample for which the sample mean is between those two values is 1 minus alpha if the null hypothesis is true. Now, notice that the lower endpoint, mu sub 0, the hypothesized value of mu, minus z sub alpha over 2 times sigma over the square root of the sample size, that is a fixed number. It's not a random variable, it's a constant. Likewise, the upper endpoint, that is a fixed constant as well. On the other hand, x bar is a random variable. It's going to vary from one sample to another. Now, I would also point out that the interval that is represented by this lower endpoint and the upper endpoint, this is an interval that is centered at mu sub 0, the hypothesized value of mu, and it goes a distance to the left and to the right of mu sub 0, a distance equal to what is really the margin of error of x bar. And so what this is telling us is that if the null hypothesis is true, then the probability that we get a hold of a sample for which the mean, the sample mean, is within this distance of mu sub 0, that probability is going to be 1 minus alpha. And if alpha is fairly small, then 1 minus alpha is going to be large. It'll be big, close to 1. And so then we see that there will be a high probability, if the null hypothesis is true, there's going to be a high probability that we get a hold of a sample that x bar, for which x bar is fairly close to mu sub 0. Now, for a particular example, the probability of, if the null hypothesis is true, the probability of getting a hold of a sample for which the sample mean is between mu sub 0 minus 1.96 times sigma over the square root of the sample size and mu sub 0 plus 1.96 times sigma over the square root of the sample size, that probability is 0.95, rather large. Another way to say this is that if the null hypothesis is true, then the probability that we obtain a sample from the population of size n, for which the sample mean is within 1.96 standard errors of mu sub 0, that probability will be 0.95. Now, by the complement rule, the probability that we get a hold of a sample for which this event does not occur will be 1 minus 0.95, and so that the probability of that event is 0.05. Well, what is the complement of the event that x bar is within 1.96 standard errors of x bar from mu sub 0? Well, it's the event that either x bar is to the left of that endpoint, or if x bar is to the right of the upper endpoint. And so what this is telling us is that if the null hypothesis is true, it would be very unusual. In fact, the probability would only be 0.05 to obtain a sample for which x bar is not in the interval represented by the lower and upper endpoint. Now, for subsequent discussion, note that another way to write this event inside the parentheses is in the following way, and all we're doing is a little bit of algebra inside each of these sets of parentheses to standardize x bar. So what we're doing is subtracting mu sub 0 from both sides of the inequality, and then dividing both sides by the 1.96 times the standard error. And anyway, so when we do this, what we see is the probability that we get a hold of a sample for which the standardized version of x bar is either to the left of negative 1.96 or greater than positive 1.96, that probability is only 0.05. And so if we were to speak in terms of what constitutes unusual values for the standardized version of X bar, we would say that it would be values of the standardized version of X bar that are either to the left of negative 1.96 or greater than positive 1.96. Now let me show you a graphical representation of this particular probability statement. All right, and keep in mind that this probability statement is equivalent to each of the, well, to this probability statement up here, which is expressed in terms of X bar itself. So again, the next slide is a graphical representation of this probability statement involving the standardized version of X bar. And so let's take a look at that now. So if the null hypothesis is true, then the standardized version of X bar will be centered at 0, as this distribution is. And in fact, this is, once we standardize X bar, then the standardized version of X bar will be standard normal. And this is a standard normal distribution curve. And if the null hypothesis is true, then the standardized version of X bar will be centered at 0, which is right here. Okay? What we're showing here is, and look at my pointer. So the point, this point right here is negative 1.96. This point right here is positive 1.96. And what this statement down here is indicating, and I constructed this graph on the TI-84, and in order to get both tails shaded like this, I had to shade each of them separately. All right, and so what is represented down here in the text below the graph is what happened or the results of shading this upper tail area. And so what these statements are saying is that the area under this standard normal curve from 1.96 up to positive infinity, that shaded area is 0.025. Now likewise, and it's clear from symmetry here, that the area under the standard normal curve to the left of negative 1.96 is also going to be 0.025. And so the total area of the shaded regions in both the left and right tails is 2 times 0.025 or 0.05. And so what this tells us is that the probability, if the null hypothesis is true, then the probability that we obtain a sample for which the standardized version of X bar is either to the left of negative 1.96 or greater than positive 1.96, that probability is only 0.05. And so values of the standardized version of X bar to the left of negative 1.96 or greater than positive 1.96, we would consider those to be unusual or unlikely values if in fact the null hypothesis is true. And so this is relevant because remember, when we are testing hypotheses, what we are looking for are values of the test statistic that are unusual or unlikely under the assumption that the null hypothesis is true. And so if we can identify those values that are unusual, then we've identified those values that are going to lead us to conclude that the null hypothesis is not true. And so that is what we're doing. This graph is a representation of this probability statement on the previous slide. So continuing on. So what constitutes unusual or unlikely values of X bar when the null hypothesis is true? Well, values of X bar that are less than or to the left of this lower endpoint, or values of X bar that are greater than or to the right of this upper endpoint. So these are the values that of X bar that we would consider to be unlikely or unusual if the null hypothesis is true, because these two events have a combined probability of occurrence of only 5%. And again, that is what's represented by these shaded regions here. So such values of X bar would be inconsistent with the null hypothesis. Now, if we observe such a value of X bar, let me see here. So if we observe such a value of X bar, in particular, a value of X bar whose standardized version is either out here or up here, or expressed in terms of X bar itself, if we observe a value of X bar to the left of this lower endpoint or to the right of that upper endpoint, then what do? We have a decision to make. Now, either the null hypothesis is true, and hence we've seen a rare event, or the null hypothesis is not true, and if it's not true, the alternative hypothesis must be true. So if we observe such a value of X bar that is extreme, all right, that's unusual, that's unlikely, what would you do? What would you conclude? What would you choose to do as a strategy, all right, in drawing your conclusion? Well, these probabilistic arguments provide the basis of a strategy for choosing between the two hypotheses. Now, according to this particular decision-making strategy that we're going to talk about, we will conclude that the null hypothesis is not true when such an extreme value of X bar is observed. All right, let me say that again. The probabilistic arguments that we've been talking about provide a basis for a strategy for choosing between these two hypotheses, and the strategy that we're going to adopt is to conclude that the null hypothesis is not true when we observe such an extreme value of X bar. In particular, if X bar is either to the left of that value or greater than that value. Okay? Now, this approach, this strategy, is called the frequentist approach, all right, and is the basis for frequentist statistics. Now, note that with this approach, the probability of concluding that the null hypothesis is false when in fact it's true, all right, is only 5%. It's only 5%. Now, in general, we must always keep in mind the following about our decision making. If we conclude that the null hypothesis is true, and hence that we have seen a rare event, so in other words, if we observe a value, an extreme or unusual or unlikely value of X bar, but choose to still hold on to the belief that the null hypothesis is true, and therefore that we've seen a rare event, but the null hypothesis is really false, then that's an inferential error, and it's called an inferential error of the second kind. It's a type 2 error. And we know that the probability of a type 2 error is denoted by beta. On the other hand, if we conclude that the null hypothesis is not true, but it really is true, then that's an inferential error of the first type. It's called a type 1 error. And this, the probability of this type of error is denoted by alpha. All right, so let's think about this example, this conceptual example that we've just gone through, and let's identify the different components of a hypothesis test that we talked about when we first started talking about hypothesis testing. So in this particular context, the sample mean, X bar, is the test statistic for the test. The set of unusual or unlikely values for X bar, which were identified assuming that the null hypothesis is true, those set of unusual or unlikely values of X bar constitute the critical region or the rejection region for the test. All right, in particular, using this strategy that we're identifying here, we would conclude that the null hypothesis is false if we observe a value of x bar either less than this lower endpoint here or greater than this upper endpoint. And then associated with this test, this 5% that we've been using for this conceptual example, that represents the significance level of the test. In other words, that 5% or 0.05, that corresponds to the probability of concluding that the null hypothesis is false when in fact it's true. Like we said on the previous slide, that 5% corresponds to the significance level of the test. Now let's continue on, and let's continue with this example, but let's reframe it just slightly. And suppose that instead of working with x bar as the test statistic, we want to use and work with a standardized version of x bar. And so if we let zcalc be equal to x bar minus the hypothesized value of the population mean divided by the standard error of x bar, then we have this probability statement that we looked at previously being equivalent to the probability that zcalc, which again is this quantity, the probability that zcalc is either less than negative 1.96 or greater than positive 1.96 being equal to 0.05. And so we can restate the criterion for whether or not to reject the null hypothesis in terms of zcalc rather than x bar, so that we reject the null hypothesis when either zcalc is less than negative 1.96 or zcalc is greater than positive 1.96 is true. And so expressing the rejection criteria in this way is a little bit cleaner and a little bit simpler when we go to working problems. And so, and I would just say that again, that the rejection criteria are typically stated in this way. And so in this particular context, this slight reformation of the problem, or re-expression of how we're going to calculate a test statistic and determine the critical points. In this context, zcalc is the test statistic. The critical region or the rejection region for the test consists of the set of unusual or unlikely values for zcalc, where these probabilities are computed under the assumption that the null hypothesis is true. And again, the significance level of the test is 5%. That is, the probability of concluding that the null hypothesis is false when in fact it's true, that is the probability of a type 1 error. And again, that is denoted by alpha. So that concludes this conceptual example of a hypothesis test. What we'll do in the next lecture video is look at the specifics of hypothesis testing procedures for a population mean for a couple different scenarios. And we'll also continue looking at how to construct confidence intervals for a population mean. And then finally, we'll also look at hypothesis testing procedures for a population proportion and how to estimate the population proportion using a point estimate and also a confidence interval.